Hi everyone. In this video, you'll learn what double stars are, why they're important, and how they're studied. So double stars are nothing more than stars that look like they're close together. They might not actually be close together. They might be at very different distances from Earth. Or they might be so far away from Earth that a small separation in the sky translates to a very large separation in reality. Nevertheless, if they look like they're close together in the sky, we call them double stars. Some of them are actually close together and they're orbiting each other. So if they are close enough, they could be gravitationally bound to each other. And if they're gravitationally bound, then they're actually going around each other. Kepler's laws tell us how we can describe the orbits of stars such as these. We know that they'll be elliptical, squashy kinds of circles, and that the secondary or dimmer star will sweep out an equal area in an equal time relative to its position to the primary star. So here's the primary star, and then we imagine the secondary star traveling around this ellipse relative to the primary star. And the secondary star will sweep out the same amount of area in the same amount of time, meaning that when it's closer to the primary star, it's going to have to move faster so that this blue area is the same as this blue area swept out when the secondary star is farther away from the primary. Kepler's third law is the mathy one, and it tells us how the period of the orbit, or the time that it takes to go around, and the semi-major axis of the orbit are related to the masses of the stars. This M1 plus M2 represents the mass of the primary star plus the mass of the secondary star. And that's what we're trying to find with double stars, is solve the orbit so that we can get their masses. Knowing the masses of the stars allows astronomers to figure out important things about stars. It helps to pin down the mass-luminosity relationship that's so important in this HR diagram. This will help us find the luminosity of stars and their distance from the Earth, and not only that, but also their temperatures and stages of life. So it's very, the goal of all of this is to figure out the sum of the masses of the stars in a double star system so that they can be studied and used to refine our knowledge of this relationship. The time it takes the star, the secondary star, to go around the primary star can be minutes or it can be thousands of years. So there's a very wide variation, and we need to use past data to help us determine this, sometimes from very far in the past, often from very far in the past. But luckily, astronomers have been at this game for quite a long time, and so they've been making these plots and helping us figure this stuff out. Now, I said that we're looking at the secondary star relative to the primary star, but it looks like both of these stars are kind of both going in these elliptical paths. So the way in which these things are studied is that we put ourselves in the reference frame of the primary star. You're going to pretend like you're standing on the red star. Relative to you, the blue star is tracing out an ellipse, but the red star is stationary. So this ellipse that we're seeing the red star take is not something that we would be able to perceive if we were standing on the red star. We would only see the blue star going around like this. Just like when we're standing on the Earth is stationary relative to us, and we see other objects appearing to move around us, when in fact we're stationary relative to them. So we're going to find that ellipse. We'll consider ourselves standing on that red star. So the primary is in a fixed position. And what we do is we plot the position angle and the separation of the secondary star relative to the primary star. So we're kind of using polar coordinates for this because we're just saying like what's the angle and what's the distance apart that the two stars are. The horizontal axis here is arcseconds in right ascension, and the vertical axis is arcseconds in declination. So here's the primary or brighter star. Here are positions of the secondary star relative to the primary over the course of the past 100 years. And so that's kind of the sort of plot we're making. When you make a measurement of a double star system, you'll find the brighter star, and then you'll find the dimmer star, and then you'll figure out how far apart they are. That's the separation, and what the position angle is. So the angle of the secondary star relative to the reference frame of the primary. But we need some more direction in order to figure out how to plot that angle. So we measure from celestial north, counterclockwise from celestial north, going through east first. And just because astronomers are cruel, they don't always plot celestial north pointed up with east to the left of it. Sometimes they plot it with east to the right of it. And then you have to remember that you're going through east first, so it looks like you're going clockwise instead of counterclockwise. So here's the position angle from celestial north, plotted in the counterclockwise from celestial north. Here it is also counterclockwise from celestial north, even though it looks clockwise. And then when they want to really be cruel, which they often do, they'll put north down. And you have to remember that the position angle is relative to celestial north going through east first, like this. So it's requires some fancy footwork with the geometrical, with imagining geometrical scenarios, but keep in mind you always need to look at your compass rose when you make these measurements, and make sure that you're making them according to convention. So what are we going to do? We're going to find a double star system to observe. We'll take some images of it using Skynet. We might pick one that is thought to be what's called optical. So an optical double are two stars that are thought to not be orbiting. We might pick one that is known to be orbiting and see if our measurements agree with the orbit that has been plotted. We might pick one that doesn't have enough past observations for it to yet be characterized as orbiting or not orbiting. So we could go any of these directions. But what we'll do in any of these cases is we'll measure the separation and position angle between the stars, and then we'll write a paper in which we do some research on the past observations of the star and describe them, report how we measured our star, and document all our equipment and software and techniques that we use to do that, and then draw a conclusion regarding whether we think the star has been classified appropriately or whether we can classify it differently based on our measurement in addition to the past observations. So that's the goal. And in future videos, we'll expand on that and tell you a little more about how to pick a star system and how to actually take the images and make the measurements. Thanks for watching.